In this video, we're going to take a look at ionization energy and some of the discrepancy and the trends across the period in the periodic table and how we can use the quantum model of the atom to explain those. So if you recall, ionization energy is defined as the minimum energy required to remove an electron from a neutral gaseous element. So if we take a neutral gaseous element, we remove an electron, so it creates an X plus ion. So just showing in the picture here, we're removing one of these two electrons, so that escapes the atom, and then the other one stays there, so it becomes a positive cation. Now, we can revisit looking at Bohr's equation and calculate the energy required to move an electron in hydrogen from the first level to the infinite level. If you recall, when we did that and looked at that, that was kind of our convergence limit, and that was evidence for ionization. But we can look at this mathematically. So let's remember delta E is equal to negative K times 1 over the final squared minus 1 over the initial level squared. So plugging in our numbers, we got 2.18 times 10 to the negative 18. Now that's in joules. Remember, that's in joules. And then we go 1 over, our final would be infinity squared minus 1 over 1 squared. 1 over infinity is essentially 0 because it's 1 over a very, very large number, which is a very, very small number. So essentially it becomes 0. If we do this, then it's basically positive 2.18 times 10 to the negative 18 joules. Now, I want to change this into kilojoules per mole. So I'm going to multiply this by Avogadro's constant times 10 to the 23. The units are moles to the minus 1. And then to get it into kilojoules, I'm just going to divide this whole thing by 1,000, which gives us 1312 kilojoules per mole. This value, if you looked on the periodic table, is the first ionization energy for hydrogen. So you can do this calculation really for any element and basically essentially find out what the ionization energy is from your equation here and from those energy transitions. So kind of neat that we can calculate what the first ionization energy is for hydrogen. Okay, so also recalling what our general trend in ionization energy is. Ionization energy increases as we go up a group, or it increases as we go across a period. But let's take a look at across a period because there's actually some discrepancies here that we haven't talked about yet in any great detail. So if we look going across a period and look at sort of the first 20 elements, you'll see that ionization energy is increasing across a period. Hits this peak for the noble gases and then drops back down and then increases again across a period. But look here, there's a little bit of a blip in terms of the trends that we see. So from beryllium to boron or magnesium to aluminum, nitrogen to oxygen, and phosphorus to sulfur, it doesn't actually follow the same trend. So we can use the quantum model of the atom to explain why that is the case. So let's look first at these transitions and this little anomaly between groups 2 and group 3. So I'll do beryllium and boron, but the same argument can be applied to magnesium and aluminum. So for beryllium, if I'm just doing the shorthand notation here, it's helium and then 2s2. And then for boron, it's helium, 2s2, and then 2p1. Or just one electron in a p orbital. Now, the reason why the ionization energy for boron is a bit lower than beryllium is because this one electron in the 2px orbital is slightly further away from the nucleus than the 2s orbitals, and those electrons in the 2s orbitals are. So it's actually easier to remove this electron here. So it's easier to remove the 2p electron, which means that it actually has a lower ionization energy than beryllium does. And like I said, you can apply the same argument to the change and that anomaly between magnesium and aluminum. Looking at group 5 to 6, let's use sort of a similar argument. So nitrogen is 2s2, and then we've got 2p1, 2, 3. And then oxygen is 2s2 and then 2p4. So one in each, and then we'll double up on one. Now, what's going on here is it's actually really energetically favorable to have these all half filled. In oxygen, we have one orbital that's fully filled, and you actually have some electron repulsion going on here between those two electrons. So because those two electrons are repulsing each other, again, it's easier to remove this electron than it is to remove any that are all in half-filled shells. So that means oxygen will have a lower ionization energy than nitrogen will. Okay, so hopefully that has explained both of those different sort of anomalies we see in trends in ionization energy. That's it for this video. Let's move on to our next task.